Well, I actually work on the Center for Quantum Technologies, but I actually wanted to give you a quick whirlwind tour of like how like non-computer scientists use Python. But it kind of relies on the slides. So
can you tell a little bit about like
yeah, so my background, so basically my background in okay, so when I first heard about this PyCon in Singapore, I was pretty excited, mainly because I'm a big fan of PyCon. So you probably all know this you know, the websites where you can watch all the videos, and we basically and I thought, oh, I might as well come down and meet you all guys and then check out what Python is about. But in the end, I thought if I'm that excited to get to know what people in Singapore are using Python for, then maybe I could contribute and tell you how we are using Python. And we are, I would say, very typical scientific users of Python, but we are basically not computer scientists. So the whole idea of this talk is, or would be, depending on whether it works, is basically to show you how you can use Python in an environment where you actually have only scientists around. So I myself, I'm an experimental physicist. That means I actually work in a lab with a lot of lasers, a lot of electronics, and a lot of hardware stuff. And there's only a tiny bit of work that we're actually doing with computers. And nonetheless, as if you ask many of my colleagues, like scientists and engineers, they all tend to pick up Python quite fast. And well, I can actually basically probably give you the introduction old school, because we are scientists, so we can do that with just the whiteboard for now. So basically, so where do I work at? I work at the place which is called oh, can I do that? Okay, I fully explain. I come from a place where you actually can write on the walls, and you can write on this wall at CQT. So I apologize for the damage caused to. So you see, physicists, we are very confused. Anyway, if you basically, okay, let's do it even more old school. Let's do it with a small fiber. So I give you the introduction, and then I hope that at some point we will actually get the computer up and running. So basically, oh, that's even better. So I work at this place called CQT, which if you want to check us out, we are in Singapore, and we are about quantum mechanics. So it's quantum, and then we have this La at the end because we are in Singapore. So it's quantum La. So for the non-Singaporeans, this is a very Singaporean term. And actually, what we are working on is we are a bunch of people, computer scientists, and by computer scientists I mean the theoretical ones that prove complexity of algorithms, and theoretical physicists and experimental physicists like myself. And as you might have heard by now, on a microscopic scale, the universe sort of is described by quantum mechanics, which is a pretty weird theory, which has a lot of counterintuitive features to it. But the goal of our center, so at CQT here, is to basically study the quantumness and figure out how quantum systems work, and then trying to put them to use. And there's a theoretical and there's an experimental aspect to things. And by potentially doing these quantum technologies, you actually get some benefit over classical machines. And I think by now, most of you might have heard the big buzz that recently, for example, one of these technologies is Google. They acquired a thing that was called a quantum computer. And so the full disclaimer here is that, well, actually, nobody in our field believes that it's actually a quantum computer, but that's beyond the point. But this is potentially one of the long-term goals in our field. Now, this all sounds nice, but in the end, in the lab, we have to sort of go from okay, so this is our physical hardware setup, to okay, this is the insight about nature that I have, and this is how I control it. And everywhere in this chain of events, there's actually a lot of Python involved. And you can pretty much, I mean, I'll show you some pictures, hopefully. You can pretty much imagine for now a big room full of equipment. So we have like I mean, you're probably not used to it if you're in school or if you're a computer scientist, but we have just tables of optics, lasers, electronics, and the maze of cables that control this equipment. And so basically, Python is then used to sort of make sense of the mess. And we have 3 steps involved in our research. So one is we have this hardware. So in my case, I study sort of the interaction of atoms, which are isolated quantum systems, with light, which laser light and stuff, which can also have quantum properties. And so I want to shine various laser beams. Now let's call it different. So I want to manipulate these atoms and sort of record how they do it. So I have to send electronic pulses and stuff. And so there's the first area is just plain experimental control, which means basically you have a bunch of hardware that you have to synchronize, and it's actually quite amazing because like hundreds of little pulses that all have to happen at the same time, and it's actually quite a hard computer science program because you have hardware timing on the millisecond time scale, so real-time things. You have software timing. You have to get everything to work together. We program FPGAs. I mean, not in Python, but we do program them. We program microcontrollers, but we also program sort of like graphical user interfaces. And the worst thing about all this thing is that we as scientists, we are scientists, so we like our job, we like doing stuff, but we are not programmers. So our big problem is that we actually have 0 clue how to program. And that is actually where Python comes in a lot of the times. So in order to make something that somebody understands as a hardware that you can control, it is very important that you actually write something which is readable and accessible to other people. And so in this case, it's a hard it's a nice software engineering problem if you want, but I write it, and then 3 years later, another graduate student has to look at it, and he has 0 clue what I did, and then he's kind of amazed. And I wanted to show you a picture of a typical LabVIEW program, which if any of you has ever looked at a LabVIEW program, yes, you might as well shoot yourself. So if you it's true. Like, so basically, if you ever did this in a Python console, it sounds a bit weird writing it on a whiteboard, but never mind. If you ever did this, let's make a prompt here. If you ever did this, you will get the famous the famous Zen of Python. And among the things there is that readability really counts. And this is one of the reasons why scientists such as me pick up Python quite fast, actually, because we like the Zen of Python. So you read it, and most of the Zen of Python could be Zen of experimental physicists, except for this thing about namespaces where we always wonder what the fuck they actually are. Okay, and so this is one thing, and this is actually a major part of our work, and usually people start doing things in LabVIEW and Bash scripts, and it's as bad as it gets, and then they get frustrated and they just start redoing all the software in Python. And right now in my community in particular, there's this overwhelming feeling that we just should get our act together and have an open source experimental control platform. Okay, so that's the first part, but that's a small part. Now we have an image. The second part, which is pretty much analogous to what Wes was talking this morning about, is data analysis. Well, I wish I could erase this, but so here and this is sort of where Python really shines. Is you are able to do data analysis in a very controlled sort of way. So imagine I actually wanted to.
I don't know what is this.
Yeah, never mind. So I imagine you want to do something to your atom in a nutshell. Actually, we are trying to do these things, so we do it on a whiteboard. So let's say you have your little atom here, and then the basic procedure of an experiment is do something, and this is very complicated, and you need a lot of Python to control it. Then the second tenet is success. So you ask, did I get something? And the actual only experimental data you have is yes, you get 0 light, so 0 photons, say. And if you have no, you get, say, 5 photons. So it's a very, well, I mean, it's very fast, so it's not that bad, but it's basically a very simple experiment. You set up your old experiment, you do something to the system you're studying, and you're trying to figure out, does it happen or does it not happen in some sort of, while you vary some sort of parameters. And after that, you just look, does the atom, or ion in this case, emit light or not? And now, usually there's a probability. So it might happen, let's say, every third time, or it might not happen every third time, something like that. So then you just do 200 experiments, and at each experiment, you ask yourself, how much light do I see? I see 1 photon, 2 photons, 3 photons, and so on. And then you have a big histogram, yeah? And now you want to map that back into something which is actually an insight about nature. And this is where we rely heavily on Python. Because we do this experiment like hundreds and thousands of times, and we bin up these histograms. So then we do, say, we fix all parameters. And then we do that, you know, say, repeat this thing 200 times or so. And we get a lot of like 5, 4, 3, 5, 6 events. And then what we bin is the probability of success. So we fit this histogram. So we fit this histogram using the SciPy universe, like using NumPy, SciPy, and so on. We fit this, and we get a sort of a single probability out for a certain set of parameters. Now, the next step we do is we vary those parameters, and we get another probability of success. And I see at least an outlook. And yeah, so then we repeat this thing for different parameters, yeah. Which means we get lots of let's just say lots of these probabilities. And then we have to fit another model, and we figure out where's the maximum probability. Yeah? And again, this maximum probability is something we are interested on, because that tells us something about nature. And not only do we have to know where it is, but we also have to know, we are scientists, so we don't just quote numbers. We actually have to put accuracy on it. So we know that this maximum probability happens as 10 plus or minus 0.1. Or plus or minus, you know, better, plus or minus 1 or something like that. So you really have to know. And then once you have these values, you can compare to your theory, and you learn actually something about nature. And then basically, over the course of a month, if not a year, you gather more and more of this data, and you fit it to more and more complicated models. And in the end, we are getting there. In the end, you're getting to an answer. And this answer is usually one number, which is derived from a long set of measurements. So I skipped through all of this. So we had all of this. I want to show you something. Well, PhD comics, of course, because we're graduate students.
Markus, sorry, we couldn't set up the IPython Notebook.
Yeah, no problem. So Wes pretty much covered it already, the keynote. And OK, so this Google and NASA. And again, I want to stress, because we're trying to do outreach, this is probably not even a quantum computer, but it's good publicity. And so this is how our lab looks. So here's the living proof that I'm a hardware guy. So it's a blurred photo from like a lot of lasers. So that's part of one table. This is how a whole table looks, a tangle of mass, electronics, mostly self-built. Well, I mean, I didn't do it alone. We're a big team. And a lot of computer control needed to do that. And yeah?
Are we safe?
Yeah. We are safe. We are always safe. Like, don't worry, keep calm and carry on. Like, science is there for you. Okay, and this is the part that I'm talking about. It's the computer control, and I can't resist. I can't. So this is what we all know, and then okay, so this is the import this. I covered this, and I can't resist in making fun of LabVIEW. So this is actually my experiment control. I didn't write it, but this is how it looks in the back. And I'm pretty sure that the next generation of students will have zero knowledge what it actually means. So by rewriting these things in Python, you actually you find a lot of mistakes, and B, you make it readable. Okay, so what I told you so far is this first story we wanted to do. We measure the structure of an ion, and I told you we try to do that by counting these photons. So again, so if they're bright, you see a lot of light. So you see 5 photons here. If they're dark, you see 0 photons. And I wanted to show off a few matplotlib plots because they're important. And so that's the first fit. You fit your data. So you just fit it to something. You get one of these probabilities out. You repeat it, then you get a beautiful course, so which this basically quantum mechanics, and you just fit the center of it, and you see each of these points is one of these previous histograms, and each of these previous histograms is like hundreds of data points, and again you get another data point, and then you change some other parameter. Now each of these little guys here would be one of the previous plots, which again is a assembly of many different plots, and you fit. That's again quantum mechanics. You fit something else to it, and you find out these things, and you do that repeatedly. And in the end, this is what we published. I mean, it looks nice, a lot of matplotlib and black and white, but it tells you that the difference. So there's a big gap between what you actually measure and what in the end you're going to publish, and the big gap is basically filled by computation. So we need computing all the time. We just don't know how to do it, and so after that, after a long month of measuring and writing and modeling, you actually have measured this, and this is the octuple moment. You don't really have to worry what it is. But in the end, you put these numbers into the world, and these error bars are largely determined by SciPy. And so that means they are not arbitrary. I mean, they have some relevance to it, but you have to trust them because, like, your theorist friends are now taking this for granted and thinking that whatever the octuple moment of this particular ion is exactly 0.05. And so if you want to test the several different theories, will make different predictions, and it actually matters whether they match up or not. So where's the Python? Data munging. I think everybody that gives presentations like this, we always hide the data munging, but until we get this nice data, there's like times and times spent on just making it look nice. And then the core part of SciPy and why scientists like it is because all the fitting routines are from the 80s and written in Fortran. So nobody is ever going to rewrite their own fitting routines because there's so many mistakes you can make. So you know that they're valid, and they're like documented in the real world, like mathematical journals and so on. So it's well, the real world and mathematical journals, probably two things. But it basically means that you can have trust in it. And a lot of people use it, like these Fortran routines. And then it's open source, so you know what's under the hood. So every single step you do, you kind of know what's out there, and that's sort of the whole spirit of science. And that's why people like Python once they get used to it. So it's very hard to get them to use Python, but once they use it, they actually quite like it. And I showed you a couple of plots, and okay, this morning we heard a bit about the all exciting web technologies, but we publish in old journals. So we do a lot of plots that are meant to look nice on paper, and matplotlib is just the standard for it. And from simple exploration to like publication ready with all like fancy labels and zoom in plots and all of that, you can do it in the same tool, and that's incredibly useful. And and basically, if you read an article, you can almost guess who made the plots with Python these days, and they're usually the nicer looking plots. Okay, so the SciPy universe absolutely and definitely rocks a lot. So basically, a second part where we use Python is, so you have these experiments, and then you well, they're expensive and like difficult to build. So sometimes you just want to have an answer of, how would they behave, so that you know what to expect. And in principle, you can simulate them. And it's just, this is actually going to be about fast numerics, and this is actually a package, not written by me, but by some other physicist, and it's on a Google code. It's called Quantum Toolbox in Python. These are the two folks that did it. Great job. And it's basically simulating these quantum systems that we're trying to measure. And the syntax is easy, and for us easy, it's like the math that you're used to describe the systems. So every grad student there can just pick up this toolbox and plug in, write 10 lines of Python code and simulate the system. Under the hood, it's very easy. It's just a bunch of sparse matrix calculations. So it's incredibly simple in the outlook. However, these problems get very, very large very, very soon. So it's like if I were just want to write down actually the measurements that I did, I could probably not even solve that on the Titan supercomputer we just saw in the NVIDIA talk. So the problem with quantum mechanics is that you can't really simulate it classically, and that's basically because quantum mechanics is this weird beast of a theory. So you need, even for toy problems, you need fast routines. And then everyone is like, yeah, you need fast computations, so why do you use Python? So I think the original reason was that the syntax of this whole toolbox, how to describe it, is based on an abandoned MATLAB project, which means if you want to port it, the natural choice is Python, because it's the closest sort of syntax you have. So the original one was the cool toolbox, and I'm showing a couple of comparisons there. And this is work from the 90s, basically a one-man job, wherever he is, Ceytan. Brilliant job, but it's basically abandoned, and it's 90s technologies. So it's a very straightforward MATLAB out of the 90s kind of project. So when they ported it over, they figured out, hey, it's Python. So it's open source, it's a bit more modern, you can put it on GitHub and stuff like that. It's open source, but they also figured out in version 1 they were already faster than the MATLAB toolbox. And it came a bit as a surprise. So this Hilbert space dimension is basically how large your problem is. And you can see it has these nasty exponential growth. That means as you make your system that you want to assemble like larger and larger, it just takes more and more time. And the good old MATLAB toolbox was the red curve. And so both have an exponential growth. It's just that the Qtip, like the Python version, is much faster. So you buy yourself some time before you run into the problem that you have to buy yourself a supercomputer. Now, why is that? I mean, MATLAB should be as good as Python, if not better. But what they could do very easily in Python is to do multiprocessing, because Python is not just isolated numerical environment. It's actually a very modern programming language. So it's quite easy to do multiprocessing. They basically just imported this pool, and then it's very easy to parallelize, and everything works. And you kind of see that by just, I mean, if you have one core, I mean, it's still a bit faster. So that's thanks to NumPy and the amazing sort of integration with the basic linear algebra routines. But the real speed up you kind of get the more and more cores you do. So we were all pretty excited about that when it came out, and the whole community was happy and like, oh, we don't have to fire up MATLAB just to use the simulation toolbox. But then these guys, they came up with version 2, like after a couple of months, and I think they just learned a lot about Python. And it's a typical Python story. So you start digging into Python, and you're a scientist, you have zero clue what you're doing. But then you figure out, wait, there's Python out there, so you can actually compile your core routines to C and get a massively enhanced speedup just by doing this. And this is actually something, when you stumble across it, it kind of blows your mind, because you still have the Python syntax, but you get almost native C speed without needing to actually write C code, which is quite nice for scientists. Okay, and so that's done. And then now it's, why not use GPUs? So you've heard all about PyCuda, so you could outload those computations onto some GPU cluster, and it's a matter of changing some core routines, but the whole overall usability of that project will still be the same. And this is not yet done, because mainly we are scientists, so we can't really program. So when we try to do something on PyCuda, we run into problems very fast, so it's not very usable at that moment. But what we do know as scientists is Fortran, and Fortran is still the fastest single-threaded, if you want, compiler out there. So some people just wrote an optimized Fortran routine for some of the part of the world, and they got a speed of order the C speed of, say, a factor of 2. So if you're happy with a factor of 2, then use this Fortran. But it just tells you how amazingly diverse the whole SciPy universe actually can be. And the last story I had, and I still can do it halfway just by the browser, I hope if this has internet, is why don't you put it on the cloud? Because, I mean, I told you that these things scale miserably with computing power, with problem size. So, I mean, natively you just go to Amazon and say, okay, I fire up my big cluster for $5, and I do my calculation, and it just buys me some more computing power. And if you, by the way, if you're an academic, it's even free in Amazon. So the nice part about Python is that it's a full-fledged programming language. So we tried back in the day to put the MATLAB thing on the cloud, and it's abysmal. You don't even want to start thinking about it. Whereas in Python, there are all these tools which are completely unrelated to physics, which try to help you put computation on the cloud, which you then can hijack and do your own stuff on it, which is really amazing. I wanted to switch over to the IPython Notebook, and I think Wes done a really good job in introducing it. This thing is a game changer. It's absolutely awesome. So, but before that, I want to finish up the slides part, and then I hope I can fire up a browser, at least. And so Python rocks big time for science. I mean, this is sort of a statement for scientists which are not familiar with Python, which is probably not so many of you in the audience. But it's really good. But the one big problem we have in Python is, like, we are not programmers, yeah. So you have to kind of cater to an audience which, I mean, we don't know anything about programming. We will not chase the latest, technology. So you have to give us some head start. You have to tell us, look, this is what you should use, and this is how you can click your way through a graphical user interface. And then slowly you pick up the tools. For example, Python 2 or Python 3, I mean, can the community not just agree on something? And it used to be one of my favorite questions I got from Windows users is, how can I install pandas? Because if you don't use a distribution, I'm pretty sure you need an afternoon just to install pandas on a Windows machine, which is not the fault of pandas, it's the fault of Windows. But at least you should have some sort of, you should be able to give somebody here, it works, everything, just click this, and then you can start. And this is what MATLAB, what Mathematica, and so on, why people pay them so much money, is because it's so much easier to work with them. So we need more tools. There's a MATLAB-like IDE around. I mean, Wes also tried to hit this point, like the R guys have the tools, Python people not. Spider is good, but not yet brilliant, but hopefully they're getting there. Then there's a plotting tool called Views, or whatever you pronounced it, and it's basically just you can click your way through a plot, which is a bit like people that use Origin and stuff like that. But we also need more books, like books about just scientific programming. There's a book by Wes on pandas, which has one chapter on IPython, which everybody now reads in our institute. So we have a couple of those books around just for basically one chapter. But it sees that there's demand for these kind of introductions. We need how-tos, we need blog posts. So please, guys, whenever you write, it might be unrelated tech. So you might think, okay, this is not like crazy physicists in the lab will not pick that up. But you should bear in mind that there are people that end up using your thing which are not scientists. And whenever you write that or think about us, just remember we are really not programmers, so we don't know how to program. So don't give us all the tech talk. Just tell us, what can we do with it, and why should we buy into that idea. We are usually picking up the tools quite fast. So we mastered quantum mechanics, so why not Python? But we only do that if they're doing the job. So that's one of the complaints most of us have, for example, with this PyCuda thing. It's nice technology, but like if you're spending like weeks just figuring out how it works, then you might as well do the weeks with your calculations on non-CUDA system. Okay, so IPython. So this is more towards general audience here. If this is a quote I found in one of the lightning talks from 2011, and I agree like 200% to it. So if you're not using IPython, you're definitely doing something wrong. So even if you're not, it's especially in the scientific world, but also I think if you're just doing plain vanilla programming. And there's also the IPython Notebook, and I guess now I have to talk a little bit about the IPython Notebook instead of actually showing you an IPython Notebook. But this is actually pretty much a game changer. So it's pure awesome, and I'll tell you in a few sort of brief ideas why this is so crucial for research. So I wanted to show you. Do we have internet? Do I have internet?
Cool. Yeah, I think you. We can just open another window. I was just doing something else.
So yeah, so basically the story goes like this. So I wanted to put this simulation on the cloud. Yeah, so Python came out, and you thought like, so you basically so this is the block about the way. This is a pretty big window. So then so you fire up your IPython Notebook, and you saw a pretty amazing glimpse on it already this morning in the keynote. So that's basically I didn't really want to do that. Let me just open these. So then you basically you start playing around with it. So I mean, you're bored. Your experiment is a bit too complicated right now. You want to procrastinate. So you basically fire up this IPython shell, which right now you can't because it's not on this. And then you start playing around with this tool set, and you figure out, hey, I can without too much effort, I can sort of. So you see a couple of these features. So here, this turned into like a whole documentation. So there's a lot of text. There's some Python code. There's a lot of text, and it's actually quite nice because, for example, this Qtip, like it's a common problem in science. You want to reproduce something, so you should know which versions of everything you have. So this just puts out a nice HTML table, which everybody knows exactly what you were doing, and so then you write a bit about how do you start, and basically it's really tailored towards somebody who just wants to do that and has no idea. So you tell them, look, download this Python distribution, and then you're happy. Then register at PyCloud, which is a service built around Amazon, which basically lets you interface with the cloud. And then the basic idea is that you just import this module cloud. You have some sort of function, and you add, and then, well, you could do that locally, but then you send it to the cloud, so the whole calculation somehow gets to the cloud, and there's a server started for you, but you don't see anything of that, and you just get the result back. And this is great because this just means you don't have to learn how to program in the cloud. So actually, you can use NumPy and the like, and with a little bit of effort, you can even use your own packages. And so you basically then it's like a toy example. You think, it works, it's nice, I can get it to work. Here you see a lot of Python code and some other Python code, but it doesn't really matter because in the end you just see, okay, I can do it locally. Here I have a compute task. I do it locally, and you say it's like whatever 70 seconds on a fairly fast machine. And if you send it to the cloud, lo and behold, it looks a bit more complicated, but not very much. So it's basically the same code, and you get a speed up. It's not very brilliant because it's only 40 seconds, but that involves basically sending data somewhere to the States, I think in Oregon, and then there's some calculation and you get it back. But this is inherently scalable. So now if you were to have a task which takes days or even weeks, then you could parallelize it on the cloud. Yeah, and so once you played around with this, you kind of realize, oh, that's great. So I can write all this documentation first for myself, so that I know. So here, for example, you say, okay, I have to use this particular function in order to get something to work, and so it's basically like glorified comments. But then you figure out, oh, that might be useful for Peter and Rob, the guys who wrote Qtip. So you start writing more and more about that, but you're never leaving the IPython notebook. And then you can upload it on GitHub, which Wes mentioned before. So this is basically just uploaded on GitHub, and this is the source code. And then you get this NB viewer thing where it's just rendered as HTML, so you can tell your colleagues, hey, look, I found a great way how to do it. They can see it, and then they can even just download the code and run it. And then at the end, you're thinking, oh, now, okay, good, Peter and Rob like it, so maybe some other people like it. So then you actually start to publish the thing. And then publication, I mean, for me as a scientist, really means publish it in a journal. But it more and more means that you also do things like blog posts. So then with a single command line command, you actually turn that thing into a blog post here on Blogger. And what you have done now is sort of, and I think that's one of the amazing part of this IPython notebook, is that you can tell a story in your computation, and you take it from basically prototyping to putting it out to a large audience, and that's basically how you can communicate your research. And since I wanted to show, but right now there's no IPython notebook running, but you can also use mathematical equations in these text cells. So that basically means you can write whole physics papers on it. And there are more and more like calculations which are written in these IPython notebooks and passed around in the community. And I think this is totally going to be okay, so two things. The first thing is this: the only thing that scientists, I've told them about, have picked by themselves because it's just great. So this seems to be an UI that people like. So you have these cells and so on. They like that, and you kind of can explore, and the tool grows with you. And you don't really have to be like a really good programmer to do all that stuff. And the second thing is, like, particularly in research, this will hopefully open up the avenue to do things a bit more reproducible currently than it is. Because if I would publish this in a journal, it would be nice, and I get the calculations printed on paper. But if I want to redo them, I have to retype everything. Chances I make mistakes and stuff. So with that, I want to thank you for listening to my half-slide, half-non-slide talk. And if you have any questions, just shoot.
One of the best talks in the last 3 years, especially in the beginning, the first.
How do you do the timing for?
So there are two. So the computational part is actually quite complicated. So there are different timescales. So we have a lot of closed loop systems that stabilize things, and that's on the microsecond timescales. And then we have hardware timed, and I have to admit we use not NVIDIA. We use NI cards, which are hardware clock tasks, and then you generate tasks on them. And then, so that's a typical experiment. So you set up one experiment, which takes like 2 seconds, and you fill a buffer, and it just clocks down analog and digital signals. And but the interesting part happens when you want to react on a faster time scale to something that happens. So you have an interplay between closed loop systems like FPGAs that measure something very fast and then react to it, because your computer is limited speed-wise. And yeah, and I mean it's a really core computer science problem, because for example, the fastest thing you can do is just look up a part in a RAM, yeah, and you need to be guaranteed the latency of that, and that hasn't really changed in the last 10 years. So we are still using like old RAM for the fastest lookup that we can do. It's basically branching of, if this happens, go there, and if this happens, go there, and then do that. So it's like you can go from like this kind of programming to, I want to build a graphical user interface where the person can just analyze, publish, and then that's it. Yeah. Any more questions?
Who wants to sign up for the Center for Quantum Technologies?
Yeah, so I mean, like as I said, it's a pretty cool place, and we try to put, well, I have to say that, but we try to put on stuff on the website which is actually accessible to like a wider audience. So it's Quantum La, so in Singapore you should remember that. And yeah, and as I said, like if you Google now for a quantum computer, there's a lot of buzz around these days, and please. For your own sanity, take that with a bit of grain of salt. So these are all articles written by PR people, not by scientists.
Any more questions? Anyways, Markus.
Okay.
Thank you very much.